right? Then let's start our today's session. So I want to take the definition. Normalizer of an element. So you take a group G and an element A belongs to G. The normalizer of the element is denoted by n of A and defined as of all x belongs to G such that Ax equal to Xa. So this is called normalizer of the element. In one way, we can observe that in the group G, you are selecting those elements which satisfy the commutative property with A. So for our recognition, if you want to draw a small picture for it, so if you take, this is the group G and this is an element A. So you are considering the set of elements in G which satisfy the commutative property with respect to A. So this thing we are taking actually here. Okay. So one observation is this normalizer is always a subgroup. This normalizer is always a subgroup for the group. Okay. Please take a note of the definition. Another one is center of a group. We denote this with the symbol Z of G and it is defined as set of all x belongs to G such that Ax equal to Xa for all A belongs to G. In other way, the center is nothing but in the whole group, you are selecting the elements which satisfy commutative property to each and every element of G. That's it. Okay. So this is called center of the group. And one interesting property is center is a normal subgroup always. So which we prove the result, how center becomes the normal subgroup, we will go for the discussion in the proof, right? You take a note of this definition. Another definition is we define the quotient group. That you take a group G and a normal subgroup H. So we define the quotient group as G by H, defined as set of all cosets with respect to H. The set of all cosets with respect to H, if you consider them into one set, it will become a group. And what could be the operation here? Here, if you take that G comma dot is a group, then G by H comma dot is the quotient group. So here we need to understand that G comma dot, where we consider dot as multiplication of the elements, here we consider dot as multiplication of cosets. And how it will be performed? If you take any two cosets, let me say HA and HB, the product is defined as HAB. So H remains the same, you are simply multiplying the elements. The same thing will be done for the operation addition also. If you take the operation as plus, so HA plus HB is nothing but HA plus B. So H plus A plus B, that is actually you are doing. So here the form of the cosets is also nothing but H plus A plus H plus B. Because if you take the operation dot, the coset is formed by multiplying the subgroup with the element. If you take the operation as plus, the coset is formed by adding the set a value. Similarly, whenever you take two cosets, we will add them correspondingly as elements will be added, set will remain same. Okay? You please take a note of that. After noting, please tell. So, one interesting observation between the quotient group and the group is generally whatever the properties satisfied by the group, the same properties will be satisfied by G by H. Since G is group, G by H is also a group, and if G is abelian, then G by H is also abelian. And in that case, G by H acts as normal subgroup. Another important thing is, if G by H is abelian, G need not be abelian. You can take the counter example with matrices. So if G by H is abelian, G need not be abelian. Right? That is one interesting property. You can say that if G is the original, G by H is its mirror image. It acts as a mirror for G. For majority of the times, the properties satisfied by G will be satisfied by G by H. So if you say that G is a cyclic group, which we discuss later, G by H is also a cyclic group. So the properties satisfied by G generally will be applicable to G by H also. Okay? Clear to all? Now let us discuss some problems and concepts over this. So if you have a doubt that if G is abelian, how G by H will be abelian? If G is abelian, then G by H is abelian. Let us prove this. So, as you know, the definition of abelian group, it is just like verifying the property that xy is equal to yx. So the same thing you are verifying with the elements in G by H. But actually what G by H is, G by H is the quotient group. It contains sets only, the cosets. So you are going to verify the multiplicative property or abelian property with respect to the cosets. So if I take two cosets, HA and HB, I have to show that HA dot HB is equal to HB dot HA. This I need to show. Are you getting the idea? All of you? Yes or no? Right. So if you consider the LHS HA dot HB, as I have defined how two sets will be multiplied, the multiplication of these two cosets is nothing but HAB. Here we need to understand the fundamental thing that how G by H is defined. The quotient group is defined in such a way that set of all cosets where the element belongs to G. So if I take 1 as an element in G, 1 into H is the coset in G by H. If I take 0 as an element in G, 0 into H is the coset of G by H. Like that. So for every element in G, we will get corresponding coset in G by H. This is the basic phenomena because every coset will be formed by means of elements taking into G. So here, as you know, whenever you consider two cosets in G by H, the corresponding elements A and B belongs to G. So by closure law, A dot B belongs to G, hence the corresponding coset is HAB. As G is abelian, we can write AB is equal to BA, hence this coset is nothing but HBA, as AB equal to BA. Again, applying the coset multiplication property, it is nothing but HB into HA. Now, this condition is satisfied by the cosets if you observe. Therefore, G by H is nothing but abelian. Okay? Please take a note of that. After noting, please tell. Shall I continue? Right. So, first we prove that, as I have stated earlier, the center of a group is a normal subgroup. Let us prove this result first. So the formal definition of a center is Z of G is defined as set of all x belongs to G such that Ax equal to Xa for all A belongs to G. That means you are selecting the elements in a group which satisfy commutative property with every element in that group. That is the concept of center. Is that okay? So, as per the procedure is concerned, the pattern of showing the result is, first we have to show that it is a non-empty set. Then we have to show that it becomes a subgroup. then we have to show that it becomes a normal subgroup. This is the hierarchy in showing that center is a normal subgroup. Accepted? Everyone? Yes or no? Right. So, first of all, to show that it is a non-empty set, in the group, I have to take an element which satisfy commutative property with every element of G. Can you say that such element exists in the group? If so, what is that? Identity. Because identity element E satisfies each and every property. So, formally we write that since Ex equal to Xe for all x belongs to G, so E belongs to the center. Therefore, center is a non-empty set. So the first part is clear. To prove that it is a subgroup, what is the thing we need to check here? What is the procedure to check here? Please tell. How we should prove that it is a subgroup to the group? Can we make use of the necessary and sufficient conditions? You agree? Because if a set is given, if you want to verify that it is a subgroup or not, apart from verifying all the properties, we will verify the necessary and sufficient conditions, isn't it? So it means that if I take two elements, x1 and x2 in the center, then I need to show that x1 dot x2 inverse belong to the center. It is just like proving that AB inverse belongs to H. Could you recollect this condition? So whenever you take two elements, this value must belong to the center. So it means that as per the center definition considered, this element must satisfy the commutative property to each and every element of G. Then only it will belong to the center. So if you take an element A belongs to G, you consider the value A into x1 into x2 inverse. So this can be written as applying associative law Ax1 into x2 inverse. Since x1 belongs to the center, it satisfies the commutative property. So this can be written as x1a into x2 inverse. So again, I apply associative law. So I need to verify whether x2 inverse satisfies commutative property or not. That means I don't know whether x2 inverse belong to the center or not. Then only I can apply the commutative property. So for our convenience, let us assume that x2 inverse satisfies the commutative property. So I can write it as x1 into x2 inverse A. since we have assumed that. Again, applying associative property, you can write it as x1 x2 inverse into A. So you can observe that initially I considered x1 x2 inverse to the right hand side of A. Now it come into the left hand side of A. So it is satisfying commutative property with A, where A is any element in G. So x1 into x2 inverse is satisfying commutative property with each and every element of G. Therefore, by definition, x1 x2 inverse belong to the center. Therefore, second part is completed. It is a subgroup. So you please take a note of that. If you have any queries, you can ask. Please ask if you have any queries. After noting, please let me know. This is also one of the previous year questions. Show that center is a normal subgroup of a group. Any queries or any doubts for anybody? So here we have assumed that x2 inverse is belonging to the center. Now let us verify that whether it is true or not. So since x2 belong to the center, we have the property that ax2 is equal to x2a. This is our by default condition. So for this relation, on both sides, you multiply with x2 inverse. You do multiplication, pre-multiplication as well as post-multiplication. So this thing you can write it as x2 inverse a, x2 inverse is equal to x2 inverse x2a, x2 inverse. So applying the technique of associative law here, it is x2 inverse a into x2 inverse is equal to x2 inverse x2 into a x2 inverse. So this value becomes identity, this value becomes identity, hence you can write it as x2 inverse a equal to a x2 inverse. Therefore, whatever the element you consider in the center, its inverse is also belonging to the center, right? Therefore, we can apply the condition that x2 inverse a is equal to a x2 inverse without any confusion. Okay, you please take a note of that. Then I want to prove the third part, that is center is a normal subgroup, which I want to show. After noting, please tell. Right? Now let us prove the last property. It is normal subgroup. As per the definition considered, this is G, this is the center. So you have to show that if you take any element here and the elements here, you have to show that x, y, x inverse belong to the center. This is actually we need to show. So consider that x, y, x inverse. Please understand that as and when you take y in the center, it means that that element is satisfying commutative property to each and every element of G. So you can replace this as yx x inverse. So applying associative law, you can write like this. Because the value of x, y, x inverse is becoming equal to y, and y is a part of center, therefore this value belongs to Z of G, hence it is a normal subgroup. This is the solution, the complete result of the question. Okay? If you have any questions, you can ask. Or I will take the next model. After noting, please let me know. Right. Now, based on this center concept, let us do a small problem. You consider G is equal to set of all 2 by 2 matrices over real numbers, and I have taken the non-singular matrices. So find its center. So please take a note of that, the question part, then I discuss the approach. In the group, what we have considered, I have taken all 2 by 2 non-singular matrices over real numbers. And I need to calculate the center of the group G. And by default, the operation is multiplication. That is always we take into consideration. So here, if you observe that, if you say Z of G is the center, it means that whatever the element you take in the center, it is satisfying commutative property with each and every element of G. So if I say that I took a matrix A, B, C, D in the center, then this matrix is satisfying commutative property with each and every 2 by 2 non-singular matrix of G. So if such is the case, what could be the pattern of the elements A, B, C, D I have to choose? That is the actual objective of the question. Because I need to check if this is the matrix satisfying commutative property with each and every element of G, what could be the possible values of A, B, C, D? Okay. By default, identity matrix is always there because identity element satisfies commutative property always there. So the matrix 1001 will be there always. There is no need to check that. So apart from this, is there any other element we have to check? Clear? So by default, identity matrix belong to the center. So our intention is there exactly one element that is identity matrix in the center, or other matrices also there? If other 2 by 2 matrices are there in the center, then what are the possible values of ABCD that we need to check? Okay? Is the question tag clear? Everyone? Yes or no? So here my intention is I will take 2 by 2 matrices in G, randomly pick up some matrices I will take, so that based on the concept of center, I will check what could be the possible values of ABCD. So in the first case, I will take that ABCD into 0110 is equal to 0110 into ABCD. Because in this place, I can take any matrix. Any matrix in G I can take. So here I have considered this matrix. Now I request you to multiply LHS and RHS separately. You compare the results and tell me what could be the values of ABCD. You will get a relation between the values of ABCD. I will mention that if you multiply them, you will get B is equal to C and A is equal to D. Please check that. Please check and confirm. You multiply the matrices first and tell me. On comparison, are you able to get similar values or not? What I have mentioned there. Everyone accept with this? B is equal to C and A is equal to D? Fine. Now, I request you to check with I say that you multiply these two and give me the conclusion. Here I will say that on observation you will get A is equal to D. This thing you will get. I will say the relation as so after multiplying the matrices, you tell me whether you got that conclusion or not. You try that on your own. Is everyone trying with this phenomena? Say. Yes or no? Right. So what happens if you take a matrix ABCD in the center? So from these observations, you got that B is equal to C is equal to 0 and A is equal to D. So substituting these resolutions in this matrix, you will get that ABCD will become as so if you take any matrix of this form, then this matrix will definitely belong to the center. So those matrices, technically we call them as scalar matrices. So every scalar matrix will belong to the center in this case. Okay. So you please take a note of that. That is the conclusion of the problem. Then we discuss another interesting problem, which is based on the quotient group. If you have clear with this, I will erase the solution part. Please tell me. Shall I? Right? Is anybody has any doubts with regard to the concept of center and this problem? Say. So from the first part, you got that A is equal to C and B is equal to D. Is everyone having the same thing or something different? Right. So please check matrix multiplication one more time then. So this is the question I discuss now. So give an example of infinite group in which every element is of finite order. This is the conclusion for the previous problem. Okay. Right. So this is one interesting question asked in the previous year papers. Give an example of infinite group where each element is of finite order. So here we have to form an infinite group, and if you pick up any element in that, we have to show that its order is finite number, not infinite number. So the example we wish to take is, you take the group as rational numbers with the operation plus, and you take h as z comma plus. So this is infinite, therefore g by h is also infinite. So you accept it or not? Because g contains infinite number of rationals, so for h you will get infinite number of cosets. Therefore g by h is also infinite group. Accepted? Yes or no? So if you write the quotient group form g by h, it is nothing but q by z you are calculating actually. So this is equal to set of all z plus m by n because how we define a quotient group? So G by H generally we call set of all AH such that A belongs to G. So if you take the operation plus, G by H is nothing but set of all A plus H such that A belongs to G. So this is the operation dot, this is the operation plus. You can take left coset or right coset, whatever the case may be. So here, if you consider the quotient group Q by Z, it is nothing but element is given by, the set is formed by adding a rational number to Z. So this is the coset here, where the number belongs to the group which is nothing but Q. Okay? You please take a note of it. So I have to show that if I take this element, it has order finite. This we need to verify as per the question tag. So are you getting the context, everyone? Say. Right. Now, as per the definition of order considered, so order is nothing but if you take an element, you are applying the operation repeatedly on the element. So after finite number of steps, you should get identity, right? If such is the case, what is the operation here in this quotient group? Tell me. Say plus. So for this element, I need to apply the operation plus repeatedly for finite number of times. So after finite number of times, I should get identity. Now let me say, if you take this, what is the identity element here in a quotient group? So we need to understand that if you talk of multiplication, please check the pattern of this. If I take A here, coset will be AH. If I take 1 here, 1H is the coset. So generally, if you take E belongs to G, EH is the corresponding coset. So nothing but H is identity. So H is identity in cosets. So here the identity is nothing but Z. So after applying the operation plus for finite number of times, I should get Z. That is the thing. Right. So here what happens? You consider Z plus M by N belongs to Q by Z. So I have to add Z plus M by N for finite number of times and I should get Z. This is my actual technique. So for this, I am doing like this. So you consider this is finite number of times. So what is the number here? I am adding this for n times. So why I am adding n times? Because in the denominator I got n. So let me say if I take 5 plus 5 plus 1 plus 5, say 60 times, it is nothing but 60 into 5. Similarly, this is nothing but n into Z plus M by N. So this is equal to Z plus n into M by N. This is the value. Please check. Did you get the logic? Say. Yes or no? All of you. Are we getting the logic or not? And here, this is nothing but Z. Since please check on this result. We have proved that X belongs to H if and only if XH is equal to H is equal to HX. So as per that, M belongs to Z if and only if Z plus M equal to Z. So Z plus M is nothing but Z here. Because in M by N, M comma N belongs to Z. So whenever you write a rational number, in the rational number, the digits are nothing but integers. So from the data, this is come like this. Clear to everyone? Any doubts? Please tell. Any questions or doubts for anybody? Say. Any questions or any doubts over this part? Any questions or any doubts? See, all these are nothing but coset properties. Because so nz is nothing but adding z n times, that is nothing but z. You are not getting any different values. Clear? Is it clear now? So here we need to understand that whenever you apply a property on the coset, you are applying the property only on the element which constitutes the coset. So set is different. So h will be always remain same. We do every operation on the element which is giving the coset. Okay? Right. So just like you can take that h plus h is nothing but h. So in numbers it is different. In sets it is different. Okay? Fine. Therefore, here you have taken n times. N is a finite number. Therefore, z plus m by n has finite order. That we take. So this is the conclusion of the problem. Now let us take the other case.
You are currently the only person in this conference.
Show this problem. Please take a note of that. Have you noted? Please reply yourself. Say. is it clear for everyone or not? Fine. So this is the problem. Please take a note of this. After this, I will close the session. So this is also a previous year question problem. This is also a previous year question. Now, here you have taken the group as 2 by 2 matrices where the matrix type is taken that A, B, 0, D. So here you have taken 3 real numbers and fourth one is 0 by default. And you are saying that if you take n in this form, it will become a normal subgroup. So first of all, we prove that it is a subgroup. Because you take, so A is equal to 1B01 and B is equal to 1C01 belong to N. So you consider AB inverse. So this is nothing but 1B01 into 1C01 inverse. What could be the value there? If we calculate that, so inverse of this matrix will be 1 by AD minus BC into D minus B minus CA. This formula if you use to calculate the inverse, it is nothing but 1 by 1 into D minus B minus C A. So nothing but, so you please multiply that, what you are getting there, and give me the value. So you will get 1, 0, 0 and 1. Accepted? Say yes or no. Therefore, it is a subgroup. Now, we prove that is it a normal subgroup or not, that we need to verify here. Let us verify this. Right? So, this is the pattern of normal subgroup. So, you have taken G here and N here. So, you are taking that X inverse A. The pattern you have to consider. So, XA X inverse belongs to N or not? That we have to calculate here. Right? So, if you consider the pattern that A, B, 0, D into A, you can take the value as 1, K, 0, 1, and here you need to calculate the inverse of X, that is nothing but 1, 0, here you will get 1, and if you multiply the inverse of this part, you will get it as, please check that thing. Sorry, I should say like this. So if you calculate the inverse there, it is going to come as 1 by A, 0, 1 by D. So this is X, this is A, this is X inverse. If you multiply these three, you will get the form like this. So this belongs to N. Because the resultant matrix is coming in the form of the elements of N, where this is nothing but real number. That's why that value belongs to N. Please check that. Are you clear? Yes or no? Please say. Are you getting the logic or not? Fine. So it has a special property. So the property here is, here G is not abelian. But if you consider G by N, it is abelian. So this is abelian. So G is not abelian, but G by N is abelian. So let us prove the part that. So please take a note of this. After noting, please tell. I will give the clarity. Right? So you consider to prove that G by N is abelian, so we have to show that Nx Ny is equal to Ny Nx. So this is nothing but this thing. Immediately you can say that so this you can say that so this is the part. You please take a note of that. So if we take x is equal to a, b, c, 0, d, y is equal to The values you can take anything. So you please verify this. So if you take the values x and y here, so if you consider x, y, x inverse, y inverse, the product of the four matrices will become as 1T01. You take x is equal to a matrix of this form, y is equal to a matrix of this form which belong to G. So as per this illustration is considered, you have to prove that G by N is abelian. So you need to verify that cosets are commuting with each other. So Nx Ny is equal to Ny Nx. So it is equivalent to prove that this condition will belong to N as and when you take two values in the group. So this is satisfied here. So this example is G is not abelian, but G by N is abelian. This is the example, right? You please take a note of this part, which will be interesting. I think, are you able to consider this form? Say, by calculating yourself. So you can say that you check with numbers. So for x and y, you check with numbers for x and y. Are you getting this type of form or not? You please confirm me. Okay? You just do it now. Is the question part clear for everyone? Say, are you getting that actually or not? Any questions, any doubts for anybody? You please take a note of these things. And this part also. So if you are clear with this part, then I will wind up our today's session and we will meet on Monday, as you wish. Please tell me. Then, thanks for everyone for today.